We're only going to be discussing one topic in this video and doing some examples regarding this topic. What we're going to do is we're going to introduce, really it's our first analysis technique beyond just simply Ohm's law in order to analyze circuits here. And this is called Kirchhoff's current law. Kirchhoff's current law, which is almost always abbreviated as KCL, which is what I'm going to do from now on, states the following. The way I like to phrase it here is that the sum of the currents leaving a node is 0. Now, shorthand notation that we can use is and this is just the summation symbol here, saying if I sum up the current from k equals 1 to n of I sub k equals 0 for a given node. Now again, this is assuming that the currents are all leaving a node. There are two other ways that you can write KCL or think about it, and depending on who you talk about, they might choose these as their definitions for KCL. This is the one that I like to choose, but the other ones are equally correct, and we actually use them both depending on the problem we're analyzing. So the other two that we could look at, first one is that we could look at it as the sum of the currents entering a node is 0. And if you think about that, that makes sense. If the sum of the currents leaving a node is 0, we know we can flip the direction of all the currents, and all that does is make those currents negative, so the values are going to stay the same, except they're all going to become the negative what they currently are. So the sum of those is going to be the same, except I'd have to make the sum a negative. But negative 0, I mean, negative 0 doesn't even make sense. 0 is not positive or negative. 0 is just 0. So the sum of the currents entering a node is also 0. And this one we actually use quite a bit. This third way to think about it is that the sum of the currents entering a node equals the sum of the currents leaving a node. Now this third one is basically saying that, well, we're not drawing all the currents entering the node or all the currents leaving the node. So some of the currents are drawn to be entering the node and some of the currents are drawn to be leaving the node. And in that case, the sum of the currents entering the node has to equal the sum of the currents leaving a node. And then this is it. That's KCL right there, Kirchhoff's current law. So let's look at a couple examples here to illustrate this. So let's first look at just even kind of look at it with some boxes here. You won't even put real circuit elements in just yet. Okay, so this is a simple circuit here, and we're supposed to find Ix. Now, typically what you want to do is obviously you need to pick a node that involves this current Ix. So we really have two choices here. We could choose this node right here or this node down here because they both involve Ix. Now, we typically don't choose the bottom one. It's not that you can't, but we typically don't choose the bottom one because in later circuits we'll see that we often make this bottom our reference. In other words, we often make this bottom 0 volts. And so we often don't deal with using the bottom wire very much. It's not that it's wrong. We could do that and we get the same answer. But what we're going to do instead is, again, look at this node here. And we need to recognize that this is all just one node. Now, if we wanted to sum the currents using we're going to go back and use our very first definition here of KCL, that the sum of the currents leaving a node is 0. So I'm going to write these currents here. So I got 3 currents here. I'm going to have I1, and then I have I2, and then I have I3. And I've drawn them all leaving the node. So we have then from that I1, this is Kirchhoff's current law, plus I2 plus I3 equals 0. Now all we have to do is kind of look at what we have here. Well, based off this picture, we can see here that I1 is equal to negative 7 amps because it's going in the opposite direction of this current right here. We can also see here that I2 is simply just Ix because it's the same current going down through this middle box here. And then I3 is clearly also going to the right here, which is 3 amps. And now we just plug these into the equation here, and we'd get negative 7 plus Ix plus 3 equals 0. And then just solving this for Ix, we quickly see that Ix is equal to 4 amps. And then we're done with the problem. Now, there's obviously other ways we could approach this, and we could approach it as the sum of the currents entering a node is 0. I'm not going to do that, but let's look at this one here. The sum of the currents entering a node equals the sum of the currents leaving a node. Well, I'm going to do this. I'm going to do this in blue here. This picture is getting a little bit messy, but I'm going to notice here that this current already here would be coming up and entering the node. So I'm going to call this current IA, and then I'll still go ahead and draw my current leaving here because I'm drawing it in the same direction of Ix. I'll call that IB, and then I'll just draw it again in the same direction of the current that I already have is IC. So when I'm doing it this way, using the third one, I'm not changing any of the directions of the currents that I'm given. I'm just kind of, keeping them the same way. And so in this case, I'd have IA, because that's entering the node, and that's going to equal the currents leaving the node, which the currents leaving the node are IB and IC. Now doing the same substitutions for these, I won't belabor this anymore. We'd get 7 is equal to Ix plus 3, which again, if we solve this, we get 4 amps is equal to Ix. And again, this is just illustrating that, of course, there is more than one way to tackle these problems. It doesn't matter which way you do it. I tend to always do currents leaving often, but depending on the problem, I will sometimes do currents entering is equal to the currents leaving. I almost never do this second one. It's not that it's wrong, I just almost never do it, that the sum of the currents entering a node is 0. Alright, so let's look at another example here. correctly that I'm copying from my notes here. Okay, so let me write it the way I have it in my notes. The 2-volt power supply is delivering 7 amps. What is the current I2? So let's draw on the circuit here what we're given. So this means I have current coming up out of the power supply, this voltage source, so I have current coming up, and then it would go over through this resistor, and it's 7 amps. And as a side note, for those of you who are thinking about practical things, yes, 7 amps and all these numbers are very large as far as currents, but we often sometimes choose some what would be maybe not standard currents that you would necessarily be measuring to make computations easier. Alright, so 7 amps is coming up and going through this resistor, and then we have to find I2. I should also state that this direction here, I missed giving you that 1 amp is going down. That's the current through resistor 3. So we're supposed to find I2, and in this case, again, I would just draw a single node right here. And remember, this node connects both R1, R2, R3, and this 3 amp current source together. And so we know that the current leaving that node is equal to 0, or in this case, because I have some arrows already drawn entering and some arrows drawn leaving, why don't we just do the current entering the node is equal to the current leaving the node. And first off, well, without writing all of these down here, I'll go ahead and say, well, we know that 7 amps is coming in, so I have 7 amps. What else is coming in to the node? Well, looking at this, we also have 3 amps with the arrow going up, so I have 3 amps coming into this node. So I have plus 3 amps. Now that's all the current that's entering the node. Now if we look at the current leaving the node, of course, we have I2 leaving, which is the current we're looking for, of course. And then R3, the problem told us that there was 1 amp going through resistor 3, so we have plus 1. And so then we get 10 is equal to I2 plus 1, and very simple computation, we see that I2 is equal to 9 amps. And that's all there is on these problems. So honestly, these beginning KCL problems, you might say, well, these are pretty easy, and they are supposed to be pretty easy. They're not supposed to be tricky. We will be getting into some more difficult things later on, but they're not supposed to be like, oh my gosh, what's going on? It's a simple concept, and we're really just trying to make sure we understand it with some basic examples. One final side note, the reason we can get KCL, if you think about it, is it's really kind of a conservation of energy kind of thing. So it's like, you know, these things can't just store current. Current has to constantly be flowing through it. There's no, quote, well for the current to build up. So because there's no well in a node for the current to build up, you know, any kind of current coming in the node has to also be the current leaving the node. And that's kind of a hand-waving, you know, argument on why that works.